Hello, everyone. Welcome to the annual holiday message from the Mindscape podcast. I'm your host, Sean Carroll. Those of you who've been listening for a while know that we have a pattern near the end of the year. I, roughly speaking, take 2 weeks off around Christmas and New Year's, where I don't do either a regular podcast or an Ask Me Anything episode for those who support on Patreon. And the last podcast of the year, rather than me interviewing someone or doing some kind of formal, careful solo episode, I just do a holiday message. And, the holiday message, I think my original idea was it would be 10 minutes long and I would say some of the highlights of what had happened during the year and so forth. But as happens when I do things, it's sort of expanded. And now sort of I pick a topic that is much more casual and maybe more personal than a little bit less intellectual, perhaps, than some of the things I would normally do on the podcast. And I just chat about it. Okay. So I'm not going to get much of an overview of the year here. It's been quite a year, 2020, in various ways. I'm not going to go into that. You've probably had various ways in which it's been quite a year for you, too. So you can imagine just running through the highlights yourself. Instead, I thought I would take this opportunity to talk about part of the practice of doing science. In particular, I'm going to talk about the phenomenon known as the Screwy universe. This is the idea that photons emitted from distant galaxies or the cosmic microwave background very, very far away can actually be rotated as they travel through empty space. Let me be clear. Sorry, let me be correct first. The polarization of these photons can be rotated as they travel through empty space. So a photon, can be thought of as an electromagnetic wave, right? And an electromagnetic wave is literally an electric field oscillating up and down, and a magnetic field oscillating backward and forward, perpendicular to the electric field. And both of those two things are perpendicular to the momentum of the electromagnetic wave traveling in some direction. So if you just ignore the magnetic field and you look along the line of the direction in which the photon is coming from, the electric field is oscillating up and down in some direction. Okay, that's the polarization. Every photon that you get, or even any classical electromagnetic wave, has an orientation when you look at it in the sky. Its polarization is pointed in some direction. Okay. If you have lots of light from an incoherent source, it can all sort of cancel out and you can have essentially zero polarization. But an individual photon is polarized in some direction, and some particular astrophysical sources have a non-zero overall polarization. Now, if the laws of physics were governed by ordinary 19th century Maxwell's equations, then the polarization just stays constant as the photon travels to you, okay? But there are some slightly more avant-garde versions of physics where you add some new fields in there, where you mess with it a little bit, in which these polarizations can rotate. And there's two reasons why this is an interesting thing to talk about right now. Number one, it has personal resonance for me because this phenomenon in the cosmological context was, I think, first mentioned in my first ever published paper. So I've been thinking about this for a long time, for a sad number of decades now, in fact. And so I thought I could share with you some of why we were even thinking about that back in my early graduate student days. And secondly, because there is now a claim on the market, I think the first credible claim I've ever heard, that this might be true. In other words, that this might actually have been detected, in particular in observations of the cosmic microwave background. There's been a recent paper by Yuto Minami and Ichiro Komatsu, which says that they've looked very carefully at the Planck telescope data of the cosmic microwave background, and they found some evidence. It's tentative evidence. I mean, maybe people on Twitter are arguing, should you even call it have evidence? It's a hint. It's a little tiny suggestion of an indication that maybe there's a bit of rotation. The technical term here is birefringence, or cosmic birefringence, this rotation of photons as they get to us. And so is that true? What would it mean if it were true? Should we trust it? What should our priors be as good Bayesians and things like that? There's been some discussion of this on Twitter and elsewhere. Brian Keating, who's a cosmologist at UC San Diego, he has a podcast and he invited me on and we discussed that. So I'll link to that in the show notes, and I'll also link to the actual paper, which has appeared in physical review letters from Minami and Komatsu, so you can read it and judge for yourself. And Ichiro also gave a talk on it, so I will link to that as well. The whole story, which now extends over 30 years, is a very interesting story of how we make progress in science. A relatively low-key story. It's not, big Nobel Prize-winning news or anything like that, but I've been there in the ground floor for this particular story, and if it's true, if it actually turns out to be true, then it would be huge news. There would be Nobel Prizes handed out, probably not to me, but you never know. And whether or not there's prizes handed out, it would be absolutely an indication of physics beyond the standard model of particle physics, which is something we're all trying to find in any way we can. So again, I wouldn't get too excited about it. I would, not in the sense that it's not exciting, but in the sense that you should wait to see what happens. But this little end of the year holiday message podcast will bring you up to speed, both sort of why you should care about this, why it's interesting, what kind of attitude you should have toward it, and at the same time give me an excuse to be a little self-indulgent and tell you some interesting episodes in my scientific biography. So with that, let's go. Imagine, if you will, your humble correspondent arriving into graduate school at Harvard University in September of 1988. So my own personal trajectory to become a scientist and so forth has been rather unusual, not the straight line path, let's just put it that way. And it's always been like that. It's never been the royal road in any sense. So it was already weird for a couple of reasons. And since I already told you I'm going to be self-indulgent, I will let you know what these reasons are. I went as an undergraduate to Villanova University, a Catholic school on the main line outside Philadelphia. And in many ways, Villanova was a wonderful place. But, really, to be perfectly honest, the reason why I went there, in addition to the fact that it had a pretty good astronomy department, was that it was free. They offered me a full academic scholarship, which most places just don't do, giving out full academic scholarships. And even back then, college was expensive. And, we were in that difficult zone where you didn't make enough money to get financial aid, but you also didn't make enough money to afford paying for college. So this was a good way to go to college, get an education on the cheap, and it was fun. I did a lot of fun things at Villanova. I found philosophy, for one thing. I became a philosophy minor. I discovered my interest in that because there were required courses in philosophy. But also, I did a little bit of research. I did research with Ed Guinan and other people who was my professor, my advisor. But it was research on, variable stars, right? We would take data on the light curves of variable stars, and we would look to try to analyze what was going on in the stars. Even back then, I knew that wasn't what I wanted to do for a living. I wanted to do theoretical physics. I had known that since I was 10 years old. It's just that at Villanova, at the time, the astronomy department was just better in various ways than the physics department, one of which was you just got to do research right away. So that's what I did. And I figured it's not that big a deal, right? I mean, you take the same physics courses, whether you're an astronomy major or a physics major. So once I went to graduate school, I figured I would just go into a physics department. But there was, unbeknownst to me, there were some unfortunate sides of that, or there were some disadvantages of being there. For one thing, there were no graduate students at Villanova, right? There was no graduate program in physics or astronomy. So on the one hand, you get extra attention from the faculty, but on the other hand, you don't get any wisdom from, if you're an undergraduate, you don't get to talk to grad students or postdocs or even faculty who are active in getting students into graduate school. So there was so much I didn't know about anything, the importance of taking the GREs. I didn't even know that you got a stipend for going to graduate school. So as soon as I looked at the tuition costs at the various places I wanted to go, I thought instantly, oh no, I'm not going to be able to do this. This is a big problem. What am I going to do? For those of you out there, if you want to be a graduate student in physics or astronomy or any of the hard sciences, there's enough grant money floating around that essentially no graduate student actually pays for tuition. You either get some sort of fellowship that pays your way if you're lucky. If you're not lucky, you're a teaching assistant and you earn your way. But one way or the other, you actually make money. It's a tiny amount of money, but you make a little money going to graduate school. And as a graduate student in a PhD program, in science, you do not come out with student debt. I had my undergraduate student debt for quite a few years because even though tuition was free, the rest of the package was not. So that's another podcast for another time. Anyway, eventually I did get to the point where I was a senior and I applied for graduate schools, and I only applied for physics departments. I knew I wanted to be a theoretical physicist. I was ready to make that switch. And I applied to a bunch of places, and I did sort of okay. I got into some, I didn't get into others. And perhaps unsurprisingly, the ones that didn't accept me were the ones I really wanted to go to. And I think that I really wanted to go to them even before they didn't accept me. I don't think it was just that they became more attractive. But in particular, Harvard and Princeton were my top two choices. Probably not in that order. Like I had some vague feeling I wanted to go to Princeton and do string theory at the time. But whereas Harvard didn't have many string theorists at the time, they had one young person, Kumran Vafa, who's now become world famous, but I didn't know any of those details. So Harvard put me on the waiting list, and I didn't really know what that meant. And in fact, I actually took a train up there on my own dime to talk to people, and it was explained to me what being on the waiting list means is that we think you're good enough to be here, but we don't have room for you, okay? We can't afford you because, like I said, there's all this money that goes into paying graduate students, and so there is a budget. They let too many people in, they just won't be able to pay them, which makes sense. So they did, sort of hint if I got my own kind of fellowship, so I was free, then they would let me in. That means more than a hint. They actually said that out loud. And actually, by the time I got home on the train, I got a letter from the National Science Foundation saying that I had a fellowship, that the NSF was giving me a graduate fellowship and they would pay for me to go to graduate school. So I waited a couple days, eagerly anticipating a notice from Harvard, and didn't get that. And eventually I sort of contacted them again, and they said, yeah, we're still thinking about it. We've never accepted anyone here from Villanova before, so we're not quite sure what to do. So that was a bit of a blow. I wasn't quite sure what to do about that. I had very other good options to go to, but still, part of me wanted to go to Harvard. And there's some romance to going to Harvard, which I have to say, once I went there, it's real. I really, had a very special experience when I eventually went to Harvard. So you might want to know, how did I get in if they didn't want to let me in? Well, the answer is between my junior and senior year at Villanova as an undergraduate, I spent a summer at the Harvard-Smithsonian Center for Astrophysics. So you have to know that the astronomy department at Harvard is associated with something called the Harvard College Observatory, which probably literally in the 1800s was, meant the telescope, right? There were people who were hired to do astronomy separate from the astronomy department, although they were related to each other. But it's sometime, I guess in the early 1970s, the Harvard College Observatory joined forces. It merged with the Smithsonian Astrophysical Observatory to found this gigantic collection of people doing research in astronomy. I think the biggest collection, certainly in the United States, is at the Harvard-Smithsonian Center for Astrophysics. So I had done research there with Sally Balunis, who was a former Villanova undergraduate, 20 years prior. So she had been a Villanova undergraduate, had kept in touch with Ed Guinan, my advisor at Villanova, and so forth. And so over the summer, I got to travel to Cambridge and did research with her, again, on variable stars. That's what they did. Got to know, that's part of why I really wanted to go to Harvard. As a graduate student, I just fell in love with the place while I was there. So I called up Sally and I said, the physics department seems to be giving me the runaround here. Is there any chance that the astronomy department at Harvard would let me in, even though I didn't apply? And she said, well, I don't know. I'm not even in the astronomy department. She was one of the Smithsonian people. But she walked over to the office of Josh Grindley, who was a Harvard professor and chair of the astronomy department, and explained to him that I had funding all by myself, and I wanted the astronomy to be a graduate student in the astronomy department. And Shah said, well, why doesn't the physics department let them in? Is there something wrong with him? And she said, no, there's something wrong with them. So Josh, to his enormous credit, he never heard of me before. It was literally 2 days before the deadline for the last, people to accept their graduate school offers. And he went to the physics department, which is a schlep because it was a 15-minute walk away. The astronomy department is separate from everything else at Harvard. Got my file, brought it around to all of the members of the graduate admissions committee in the astronomy department, got them to sign off, and accepted me. And he said he would do this on one condition. He called me up and he said, look, I'm only going to do this if you say, if we let you in, you will come. And so I said, sure, I want to come. And that's what I did. So that's why in September of 1988, I ended up in the astronomy department as a new graduate student at Harvard. And again, much like an undergraduate, I could still take all the physics course I wanted to take. So, and I ended up over the course of my 5 years at Harvard taking lots of physics courses. I even taught a general relativity course together with my friend Ted Pine to the other grad students at the astronomy department at Harvard. And the notes for that lectures that we gave as graduate students eventually evolved into the textbook that I wrote, Spacetime and Geometry. And so I also took courses over at MIT and ended up working with people at MIT like Eddie Fari and Alan Guth and so forth. And so it was a wonderful experience overall. But at the time, right, when I'm brand new, I didn't know anything, and it was all very scary. It was all very intimidating. And one thing that happens is one of the nice things about the astronomy department at Harvard for incoming grad students is exactly because of this Harvard Smithsonian Center for Astrophysics, there's a huge number of people there, a huge number of PhD astronomers doing research. Okay, so just huge amounts of resources for people who want to be astronomers and learn it and be graduate students and get a good education. So at many places, I won't name names, but at many places, you can be a grad student and you can kind of coast through, depending on how you interact with your advisor, who's the one person who really matters. They can either, drive you crazy demanding work, or they can kind of ignore you and, you can sort of drift a little bit. But at the Harvard Astronomy Department, because there were so many people there who were PhDs, they actually had what is called a PhD thesis committee that would meet every 6 months to check up on your progress. Like no place I've ever been has ever done anything like this before. But that was far off at the time. At the time, I was just assigned kind of randomly an advisor, right? Because they as soon as you arrive, they assigned you an advisor, and then you may or may not stay with that advisor to do your PhD, but they want someone there who is a faculty member to sort of keep you in line, answer questions for you, check up on how you're doing, stuff like that. So I was assigned George Field, who I had never heard of before. He was an older guy. He still is. He's still around. He's still one of my favorite people in the world. We still talk all the time, and I'll even tell you a little bit about the research we're still doing in a minute. But George, I later realized, was an extremely distinguished theoretical astrophysicist, but in sort of a specialty that I knew very little about. I mean, he had worked on the interstellar medium, the intergalactic medium, magnetic fields, galaxy formation, things like that. My interests were in sort of particle physics, general relativity, and how they applied to cosmology. But purely by accident, George had become interested in those things. So George was actually stolen away from Berkeley by Harvard because when they formed the Center for Astrophysics, right, in the 70s, when they joined the Harvard College Observatory with the Smithsonian Astrophysical Observatory, they wanted to hire a big name to be the first director, to get the place off the ground and so forth. And they hired George. George was the founding director of the Harvard Smithsonian Center for Astrophysics, but he had retired from that job a few years ago. And, he wasn't that active doing research while he was the director. He had thrown himself into being the director, bringing up this new place. And so he kind of had a little bit of a luxury when he stopped being director to pick and choose what kind of research he wanted to do. And being the kind of person he is, he didn't want to just do the same thing he had done before. He wanted to do something new. So again, being the person he is, and it was, a big influence on me and my attitude toward trying different things and lifelong learning and things like that. George said, well, what would I do if I were a student, right? And he knew about, this is the late 80s, he knew that there was a burgeoning interest in particle physics and cosmology and their intersection and so forth, using the early universe as a particle accelerator. And so he said, well, if I were a graduate student in theoretical physics, I would go to a summer school. That's this thing where you sort of go to some exotic location as a student and you hear lectures from the great people. So he did that. He went to a summer school. Over the course of his career, he'd given lectures at summer schools all the time. But here he went as a student as a summer school for quantum field theory and particle physics and theoretical physics, okay? And had a great time. The summer school was at Les Houches. I later went to a Les Houches summer school myself. It's a wonderful institution. And interestingly, it was all these lectures from particle physicists, field theorists. And, the late 80s, it's hard to exactly characterize what was going on, but it was a little bit of a slow point in theoretical particle physics, okay? We had discovered all the stuff in the Standard Model, except for, the top quark and the Higgs boson, but everyone thought we would discover those at some point. We had certainly discovered the W and the Z. And cosmology was a little bit stuck. We had not yet found the cosmic microwave background anisotropies. We were trying to measure the Hubble constant and so forth. So, it was overall a slow point. And when that happens, people's minds sort of wander a little bit and they look for interesting new problems. So one of the sets of lectures that George sat in on at his Lejus summer school was by Roman Jakiev, who was a professor at MIT, just down the road from Harvard, a very accomplished senior mathematical theoretical physicist. Roman is probably best known for being the co-discoverer of anomalies. Anomalies in quantum mechanics are when you have a classical theory that has some symmetries, but then you quantize those symmetries. The symmetries can be, when you quantize those theories, the symmetries can be broken by the process of quantization. And this actually has empirical effects, and it's been observed. And, so the Adler-Bell-Jakiev anomaly is a big deal in particle physics and quantum field theory. And for years, Roman's intellectual interests had driven him to think about physics in two dimensions. That is to say, two dimensions of space, one dimension of time. So what we often call 2 + 1 dimensions, okay? We all know that 2 + 1 = 3, but 2 + 1 dimensions means two dimensions of space, one dimension of time. And this is physically very interesting because you can make materials, right, like graphene or whatever. They didn't know about graphene at the time, but they knew you could make materials where all the interesting physics was confined to a two-dimensional plane. But it's also, for someone like Roman, who is extremely mathematical, it's mathematically fascinating because the geometry and topology and all these different things that go on in 3 dimensions are just different than in 4 dimensions. So there's a whole new mathematical playground. And so Roman gave lectures at Les Houches on his 2 + 1 dimensional physics playground. And in particular, there was a particular effect in electromagnetism, which is that in 3 + 1 dimensions in the ordinary world, there's only so much you can do with the electromagnetic field. And basically, Maxwell had done it back in the 19th century. You can always, add new particles and forces and whatever, but electromagnetism by itself was pretty cut and dried, okay? But it turns out that in 2 + 1 dimensional space-time, there is an extra term that you can write down in the equations of motion for the electromagnetic field, one that just isn't allowed in 3 + 1 dimensions. And it's called the Churn-Simons term, and that's named after S.S. Churn and Jim Simons. Jim Simons, you might know, because later he left mathematics and founded Renaissance Technologies and made a whole lot of money, let's put it that way. Renaissance Technologies tracks the prices of things, stocks and various things. I don't even know what they track, right? Bonds, I suppose, equities, and they sell them very, very rapidly and buy them on the advice of this big code that they built. And so he's made a lot of money doing that. And that's why the Simons Foundation, named after Jim Simons, is now such a good patron of physics and science more broadly and mathematics, because Jim Simons was a very accomplished mathematician before he went off and made a lot of money. So the Churn-Simons term is something that is unique to 3-dimensional manifolds. Okay, so 2 + 1 counts in this case. And what Simons and Churn had been interested in was the topology of these 3-dimensional manifolds. And so there's a specific kind of topological invariant that only works in 3 dimensions, and it's called the Churn-Simons term, okay? And if you want more details on this, I advocate that you check out my Biggest Ideas in the Universe video on geometry and topology, where I talk a little bit about it there, just a very little bit. But anyway, so Roman had taken this topological mathematical structure that Churn and Simons had invented and realized it had a use in physics. You could put it into the equations of motion for the electromagnetic field, and it would change them a little bit. It was kind of like giving the photon a mass. You all know, or you should know, or maybe you've heard, or maybe I'm telling you now for the first time, photons are massless, okay? In the real world, photons have 0 mass. And this thing you could do with the Churn-Simons term in 3 dimensions was like giving the photon a mass, but not really, okay? And I'm not going to go into details about why it wasn't really true. But anyway, it has a lot of implications for a lot of things. Still, Churn-Simons theories are incredibly interesting to mathematical physicists even today. So George is sitting there listening to Roman talk about, this term that you could write down in 2 + 1 dimensions. And in his innocent little astrophysical way, he said, But come on, I mean, if you want me to be interested in this, there has to be some way that we can do this in 3+1 dimensions in the real world. This is the difference between theoretical astrophysicists and mathematical physicists. The astrophysicist is always going to want to bring it down to the real world, okay? And the mathematical physicist is perfectly fine if the real world comes by to visit sometimes, but doesn't stay off and stay overnight or anything like that. And Roman, he thought about it and he said, look, you can't, because if you tried to, the only way to do something like that would be to pick out a preferred direction of space-time and then think of the 2+1 dimensions as being perpendicular to that preferred direction of space-time. Then you could do it. But the problem with that is that it violates Lorenz invariance. Lorenz invariance is a foundational principle of modern physics. It's what Einstein used as the bedrock for the special theory of relativity, even though it goes back earlier to Lorenz and other people, right? And it's the basic idea that you can't tell how fast you're moving. There is no preferred reference frame in space or in space-time with respect to which you can measure your velocity. So if you measure the laws of physics in one reference frame and then measure them in some other reference frame, they will look the same to you, okay? So Roman Shakib's point to George was, if you did just force yourself to make some kind of version of a Churn-Simons term in electromagnetism, but in the real world, not in this fake three-dimensional world, you would have to do it at the expense of violating Lorenz invariance. And so George's answer to that was, okay, let's do that. And again, I think that he was aided a little bit by sort of not being a working particle physicist or quantum field theorist, like the kind of thing that would just be anathema to those people. He said, well, yeah, let's try it. Let's see what happens, okay? So he convinced Roman that that would be a good idea. And that's where I came in. So that was the summer, right, before I came to Harvard. I arrived at Harvard, and the two of them had agreed to get back together and talk about this. And they each brought their graduate students. Roman's a graduate student eventually decoupled. He went somewhere else. But I, hung along for this project they wanted to work on. And this is a very typical way that as a new graduate student, you get involved in a project. Either your advisor or your advisor and their friends has some idea they're just beginning to work out, and they bring you along to sort of catch up and help them along the way. So I'm being very, very clear here, like none of the real intellectual heavy lifting on this was originally mine. I did make contributions to the paper, but it wasn't my idea. The idea came even before I arrived in Cambridge. So we sat down. I remember very vividly, we were in George's office. Roman came over, and it was all very intimidating. There were so many books with all these titles about that sort of hinted at treasures that I did not have access to because I had just begun my theoretical physics education. One of the side disadvantages of being at an undergraduate institution was not just you didn't talk to graduate students, but you didn't get to take any graduate classes, right? Most undergraduates who want to grow up to be theoretical physicists and who go to places like Caltech or Berkeley or whatever will sit in on or take graduate classes so that when they actually arrive in graduate school, they have a leg up, a little bit of an advantage. I had none of those advantages. So I didn't even take quantum field theory my first year in grad school, whereas many people take quantum field theory as juniors or seniors in undergraduate school. So catching up has been the story of my life ever since then. And it was definitely the case here because here's, Roman and George who know, even though George was not a working quantum field theorist, he knew special relativity, he knew classical field theory inside out. He knew the lingo, the jargon, the notation, the mathematical way of writing things. And he had already come up with a way that he was proposing that we could actually experimentally test this idea. So I was completely lost. I had no idea what they were talking about. They were writing equations on the blackboard. I promised myself I would go home and try to catch up and look at some books on field theory, which I ultimately did. But basically, here was the idea. What George noticed was, you can hear Caliban in the background. I think he's meowing because it's almost dinner time. Anyway. He said, look, okay, so you have what the point of this idea was when Roman said this theory would violate Lorenz invariance. One way of thinking about it is if you had been just in 2+1 dimensions, just in a three-dimensional universe, then there's a parameter. There's a number that goes into the Churn-Simons theory, which basically says how important, how big is this effect that you're adding to conventional electromagnetism. And it's just a number, right? And it's the Churn-Simons parameter. But in the real world, in 3+1 dimensions, in four-dimensional space-time, that parameter gets promoted to a vector. It points in some direction in space-time, okay? And that's why it violates Lorenz invariance. It's kind of like the ether, right? It's a universal vector field that fills all of space-time, or it would be if it existed. And it is something with respect to which you can measure. Are you in the rest frame of this vector field? It's a space-time vector field, not just a spatial vector field. So it doesn't necessarily point north, south, east, west. It can point in the time-like direction, for example. And in fact, without knowing any other specific reason why this vector field should exist at all, it would be very natural if this vector just pointed in the time-like direction with respect to the cosmological rest frame, right? We know that in special relativity, there is no preferred rest frame as far as the laws of physics are concerned. But in our real-world universe, the stuff in space-time defines a rest frame, right? We talk about we're being at rest with respect to the cosmic microwave background or the rest frame of the galaxies that we live in. Okay, so there is a natural cosmological rest frame. And if you had to pick, if you had to choose where this vector would be pointing, it would be perpendicular to surfaces of constant time in that reference frame. Okay, so you would think that, roughly speaking, your guess would be that this vector field would be completely time-like, okay? It would not, in other words, pick out a preferred direction in space. It would only pick out a preferred direction in space-time. That was a natural guess, okay? And so what George had figured out, he'd written down all the equations, and he'd gone through and he'd solved them, and he basically done undergraduate electromagnetism, but he what you would derive the propagation of electromagnetic waves, right? That's an elementary exercise you do in electromagnetism, but he did it in the presence of this new modification, this new Churn-Simons term, and he found this effect. He found that it would change the polarization state of a photon or of an electromagnetic wave. If an electromagnetic wave traveled through space, in the presence of this new Churn-Simons effect, its polarization would rotate, okay? So that's the kind of thing, like I said, any undergraduate could have done it if they'd been told to do exactly that. Part of being a good scientist is deciding what to do, what questions are interesting enough to work on, what equations you should write down and solve. So that part is hard, but once you had them there, anyone could have solved these equations. That was not really the hard part. The reason why it was very useful that we had George on this project, not only that he, pushed it forward and came up with the idea, but he said, and you know what? We can actually test this. Being a real theoretical astrophysicist, he knew about real phenomena in the universe, like galaxies and stuff like that. And here's the problem with testing this idea. You say there's some source out there in the universe. It emits a polarized beam of light traveling toward you, and it gets rotated by this effect that is these days called cosmic birefringence. Back then, we didn't know about that. It's a word borrowed from the condensed matter literature. So sure, you can rotate a polarization of a photon via cosmological birefringence, but all that says is that the polarization is different when it arrives at you than it was when it left. How do you know what it was when it left, right? Like, that's the hard part. This is often the case in astronomy. How do you know where it started? This is the classic problem of distances in astronomy. You know how bright things look, but how bright were they at their source? That would tell you if only you knew. That's the tricky part. So likewise for the polarization. But George knew that there were these things called radio galaxies. And radio galaxies are just galaxies that emit radio waves, but very, very typically, there's a reason why these galaxies are emitting radio waves. You probably have seen these pictures of black holes with jets coming out of them, right? If you have a black hole with an accretion disk around it, there's a jet of material that is ejected along the north axis and the southern axis of the black hole. And this can happen on galaxy-sized scales, right? And if you are lucky enough to be looking at the jet, you would see this as a very bright quasar. But if you're looking perpendicular to the jet, you can actually see the jet. So you can actually take a picture in a radio telescope of this galaxy on the sky, and it's not just a diffuse blob, it has a direction. There's a direction in which this jet is pushing matter away from the black hole at the center, okay? And what happens is there are magnetic fields in this jet, and they are stretched along the direction in which they're being pushed, right? So not only do you see this jet on the sky in the picture you've taken in your telescope, but you can also predict ahead of time there will be a magnetic field stretched in the same direction. Okay, and I'm going through this carefully because it matters that you know the direction of everything at the source, even though you can't go there and measure it. You need some physical intuition. Okay, and the physics tells you the magnetic field should be along the same direction, pointing in the same direction as the jet. And what happens is in that jet, there are all these electrons, and there are other charged particles, but electrons do almost all the work. And when you put an electron in a magnetic field, it sort of goes around in circles, perpendicular to the magnetic field, okay? And an electron going around in circles will emit electromagnetic waves. All the light around you, as any of you know if you heard my quantum mechanics talks, comes from electrons in motion emitting electromagnetic waves. So visualize this if you want to. On the sky, you see a jet. It's oriented in some direction. You know the magnetic field is pointing in that direction. So you know the electrons are rotating perpendicular to that direction. So they're going up and down. If the jet is oriented left and right, the electrons are circling in a way that to you looks like up and down. And when they emit an electric field, it is therefore polarized vertically up and down. The polarization of the photons or the electromagnetic waves coming from those electrons is in the same direction of their motion. Therefore, there's a very strong prediction. There is so we haven't gotten into crazy physics yet. This is ordinary astrophysics. There's a very strong intuition, expectation, prediction that the polarization of these radio jets will be perpendicular to the direction in which they're stretched along the sky, okay? So this gives you not a standard candle, but a standard polarization. This gives you something in the sky where you can look for radiation that is polarized in radio telescopes, and you know what the polarization was when it left the galaxy. So you can compare to what it is when you look for it, when you observe it here, and you can see whether or not it's been rotated, okay? So just to summarize, in case you haven't, this is a lot of material. I know it very well. I was very excited. This is the beginning of my life as a working research scientist. We had this crazy theory, Churn-Simons theory, that violates Lorenz invariants, and its experimentally testable prediction is that it causes birefringence. It rotates the polarization from photons traveling through empty space. And in these radio galaxies, you have a source where you know what the polarization was, so you can test it. And furthermore, the more the photon travels through empty space, the more rotation you predict, right? So not only can you just look at a bunch of radio galaxies, but you can look at radio galaxies as a function of distance. And if this effect were real, you would think that radio galaxies nearby should have almost no rotation, whereas radio galaxies far away should have a lot of rotation, a lot of birefringence. That's where the graduate student comes in. This was my job. My job was to go through the literature. And, back then we didn't even have computers on our desks. You had to actually go through the journal, print it on pieces of paper and Xerox them and, type them into a terminal somewhere. And so I had to find a bunch of data, not only for the polarization of radio galaxies, but also for their distances. And this was very exciting to me, and I did it while, at night trying to learn enough about field theory to understand what in the world we were doing. And I did it, and I found 160 galaxies where I could get both the polarization data and the distance data. And I plotted them, and I learned how to make plots in the software that we had available to us at CFA. And lo and behold, there was no effect. Okay, don't get your hopes up here. We put a limit on it, right? That's what you can do. That's what we expected to do. There was zero, none of us ever thought, there was zero expectation that we would find a non-zero rotation, okay? We were trying to put a limit on it. So here's where I can step back and say, why would you do that? Like, why would you work so hard? Not that hard, but you work a little bit hard on showing that something you expect to be zero is zero. Well, it's a high risk, high reward kind of thing, right? On the one hand, we didn't expect it to be a non-zero effect in the data. But on the other hand, if it had been, it would have been huge, right? Violating Lorenz invariants. Oh my goodness. And in fact, at that time, 1988, there weren't a lot of experimental tests of Lorenz invariants, okay? I mean, there were some sort of model-independent tests of Lorenz invariants. In other words, you just come up with some experiment and then you rotate it or you move it at some speed and do it again. But there wasn't any systematic investigation of ways the Lorenz invariants could reasonably be broken. So the really nice, cool thing about this Churn-Simons theory was, even though it broke Lorenz invariants, it didn't break anything else. It didn't break gauge invariance or charge conservation or anything like that. For other reasons, otherwise it was a perfectly respectable theory. There were some worries about, I'll get to in a second, there were some worries about the fact that you could maybe violate energy conservation. You could sort of create energy from this rigid background vector field, but that turns out to be a fixable problem. And interestingly, like I was learning enough about what other people kind of did in research-wise in theoretical physics to know that what we were doing was a little bit disreputable. Violating Lorenz invariants. No one else did that. But to everyone's surprise, nowadays, right, a certain number of decades later, that paper that we ended up writing, which ended up being my first ever published paper. I had another paper that I did as an undergraduate, but we were so slow doing that one that it didn't come out until after our Churn-Simons paper. It has like well over 1,000 citations. It really sort of launched not just investigations into cosmological birefringence, but really the whole program of inventing reasonable ways of violating Lorenz invariants and then testing them experimentally. And it's a good lesson because, even though the theories themselves were certainly speculative, they were all very experimentally testable in different ways, some of them with ground-based experiments, some of them with astrophysical experiments. And that's always something that physicists are going to like to do, because even if you think that it's unlikely you'll find an effect, finding it is really, really important. And sometimes you just have to go on a fishing expedition and see what's out there. Okay. So these days, there's huge numbers of people and experimental teams trying to test Lorenz invariants in various ways. And I think it's true that, we were the first paper that sort of had a respectable field theory basis for how Lorenz invariants could be violated and then tested. Okay. So, it was much more respectable in retrospect than I thought it was at the time. But anyway, I actually did the sort of computing here, right? Like I learned enough statistics to learn how to test our hypothesis, showed that it was not, there was no evidence that there was any birefringence, put limits on it, okay? There's a numerical limit we could put on it. And numerically, that limit works out to be roughly the size of the universe because we were looking at galaxies that were roughly the size of the universe away. Okay. So we could have left it there, and roughly speaking, we did leave it there. I think Roman left it there. He moved on to other things. But George and I were always bugged by the fact that, the physical manifestation that we were testing was kind of cool, right? These photons moving around, having their polarizations rotated. But the theoretical justification for it was entirely pulled out of a hat. Just have a vector field out there in space, whatever. So we thought about what that meant and where it could come from. And it turns out there's sort of a more respectable version of almost exactly the same theory. And that is, instead of having a vector field, have a scalar field, okay? So the difference is that what a scalar field means is that at every point in space, there's a value to the field. But for a vector field, there is a value and also a direction, right? A vector, just think of a little arrow pointing in space-time. It has a magnitude and also a direction. A scalar field just has a magnitude. It's just a number at every point in space, like the temperature of the air in a room. At every point, there's a temperature. Okay, that's a scalar field. But we're imagining a fundamental scalar field, right? Like imagine that there is some new ingredient to nature, this scalar field, and we're imagining this scalar field rolls down a hill. This is something that quantum field theorists and particle physicists and cosmologists do all the time. The Higgs boson relies on this idea. You imagine there's a potential for your scalar field, and the field wants to roll down to the bottom of the potential like a ball rolling to the bottom of a hill, okay? The difference is, for something like the Higgs boson, the Higgs has a potential and it rolls down to the bottom, but it rolls down very, very quickly in some tiny fraction of a second. We were imagining a hill that was very, very gentle So our scalar field would roll down it, but it would take the lifetime of the universe. It would take over 10 billion years to actually move in any substantial way, okay? What does this have to do with our Chern-Simons theory? Well, you can take this vector field changing with time, and in principle, it could change with space, right? And so by doing calculus to it, you could say, well, what is the gradient of this scalar field? What is the vector that defines the magnitude and direction in which it is changing? So if the scalar field is the same value everywhere in space but is changing in time, it has a gradient that is purely time-like, a vector that is pointing purely in the time-like direction. Whereas if the scalar field were not changing in time at all, but were changing in some direction in space, then its gradient would be purely space-like and all the different possible things in between. So it turns out that the idea of a scalar field, in fact, technically speaking, it would be called a pseudo-scalar field because it's a parity, it has negative parity instead of positive parity. I'm not going to talk about what that means. In fact, as I'm saying it, I realize if you're not a physicist, you might think I'm saying P-A-R-O-D-Y parity. I'm actually saying P-A-R-I-T-Y parity, the how things act when you show them in a mirror or something like that, okay? So if you looked at this scalar field in a mirror, it would go to minus its own value. That's what it means to be a pseudo-scalar field. So the reason why I'm saying this is because there has been way before we came along, there were this idea that there could be scalar fields that coupled to electromagnetism in exactly the same way as our vector field did if you just talked about the gradient instead of talking about the field itself. So literally the pion, if you think about the pion particle as a scalar field, it couples to photons in exactly this way. The axion, which is a hypothetical particle, but axions also couple to electromagnetism in this way. The only difference, the real difference in what we were caring about was, again, this particular pseudoscalar field that we were inventing would evolve over cosmological timescales, okay? It would not rush to hit the bottom of its potential and just sit there. It would slowly evolve over cosmic time. And so we wrote a paper about that, and then we wrote various other papers, just a couple other papers, because we realized that if you did have, in the early universe, this kind of pseudoscalar field rapidly evolving, it could dump its energy into the electromagnetic field and therefore be a source of magnetogenesis. It could create magnetic fields in the early universe. And that's a good thing to do because there are magnetic fields in the late universe now, and we're not completely sure where they came from. So I told you I was going to say what George and I were still thinking about. We were still thinking about specific models in which you can create magnetic fields in the early universe from some rolling pseudoscalar field in exactly this way, using exactly this coupling. Okay, but most of the research that I did and George did and Roman did subsequent to then had nothing to do with this particular Churn-Simons theory or anything like that. You know, we moved on to other things, and other people got very excited about Lorenz invariants, but I was not really paying that much attention to it. So now move forward 7 years, okay? So 1990, so I said in 1988 I arrived at Harvard, but our paper, it takes time to write, and then it takes a year to get through the refereeing and so forth. It technically appeared in 1990. So 7 years after that, in 1997, I was already on my second postdoc. So I had gotten my PhD. I'd done a first postdoc at MIT for 3 years, and I was on my second postdoc in Santa Barbara, okay, at the Institute for Theoretical Physics, now the Kavli Institute for Theoretical Physics, the KITP. And it was a wonderful time, but I was beginning to realize that I was in trouble, okay? Because, like I said, in 1988, or even, 4 or 5 years later, there wasn't a lot exciting going on in theoretical particle physics and cosmology. And so I did perfectly well just doing things I thought were cool, right? Violating the Lorenz invariants. I worked on time machines in general relativity. I worked on textures and other topological defects, stuff like that. Supergravity, just a grab bag of different things. But by the time it was 1997, things had happened that were really exciting. In cosmology, we had discovered in 1992, the COBE satellite had discovered the anisotropies of the cosmic microwave background. And people were very, very excited in cosmology about using the microwave background, the CMB, to test cosmological models to constrain parameters of the universe. So there was a whole bandwagon of people who had leapt on that, and I was not on that bandwagon. Meanwhile, on the theoretical particle physics side of things, people had discovered dualities. And so Witten and Seiberg had discovered in supersymmetry and supergravity, there were these duality relationships. And then Joe Polchinski used that in string theory to invent D-branes and string theory duality. And then Juan Maldacena found the ADS-CFT duality and so forth. And so everyone on that side of the ledger was working on dualities and the second superstring revolution. And I was not working in any of these exciting areas. And I know that there's a certain romantic component to being a professional academic that says, well, you should just work on what interests you. But as I tell my students, you should really work on the intersection of what interests you and what interests the rest of the world. And that the interest of the rest of the world had shifted, and I had not shifted along with it. So when I applied for my first postdoc, I was a hot property on the postdoc market. But when I applied for my second, I was not. And here, 1997, I should be applying for faculty jobs, and I was not a hot property on the job market, which is a polite way or a sensationalized way of saying I was not getting any jobs. I was not even getting on any shortlists for any faculty jobs. So I realized that I needed to think of ways which I could write papers that I cared about, that I thought were interesting, but that the rest of the world also thought were interesting. And I wasn't that excited about either the microwave background or the second superstring revolution, so I was a little bit stuck. So just by accident, in 1997, I got an email from George Field. And he said, yeah, you should read this story on the front page of the New York Times about this finding in cosmology. And so I said, okay, sure. You know, he was in Cambridge, Massachusetts. I was in California. I said, okay, I'll read it at some point. And then the next day he emails me again. He says, no, you really got to read this right now. It's kind of important. So I said, okay. I read it. And then I read the story in the New York Times, the front page, not just the front page of the Science Times, literally the front page of the New York Times. And it says, you know, I forget the title of it. It was something like, you know, astronomers find evidence for preferred direction in space or something like that, okay? And, you know, something like, you know, when you read stories in the popular press, it's perfectly okay that they get excited about claims that would be dramatic if they were true, but you need to be able to sort of normalize them and say, but they're probably not true. You have to be able to judge a little bit what claims are worth taking seriously. And just the fact that something appeared in the New York Times is not enough to make me take it seriously. But on George's recommendation, I read it, and I instantly realized something, that this paper, which talked with this article in the New York Times, which talked about a new finding by two scientists who I didn't know personally, Borge Nodland and Joseph Ralston, had looked at data of polarized radio galaxies. And in fact, when I looked closely, it said that they had 160 radio galaxies. And since it had been my first ever published paper 7 years before, I knew that number 160. That's the number of radio galaxies who I had typed in when I was a young graduate student when we wrote our paper. It seemed to me that it was too much of a coincidence if they had the same number of radio galaxies for doing something very different. So I downloaded their actual paper. By then, you know, the internet was all the rage, and we had the archive. You can just find the paper, okay? And here's what they had done, Nodland and Ralston. They had looked at exactly our data set, right? And we didn't collect the data, so it's not our data set, but the data that we looked at. But what George and Roman and I had done was just look, you know, for our simplicity and peace of mind, we assumed that this vector field that we were trying to constrain was time-like, right? I talked about the fact that you have a vector field in space-time. It could be space-like or time-like or whatever. Just to make things simple, we imagined that it was purely time-like, and then we constrained that. So we could easily have looked for space-like effects, and that would be, so what we had predicted was that all throughout the sky, if this effect were real, there'd be a rotation either clockwise or counterclockwise, but by some definite amount everywhere, except that farther away galaxies would have a bigger effect, okay? So we would get either every galaxy in the universe would be rotated in its polarization clockwise by a little bit, or every galaxy in the universe would have its polarization of its photons rotated counterclockwise by a little bit, or something like that, okay? That's what you would expect for a time-like vector field violating Lorenz invariance. If you have a space-like vector field, that means you're literally having a preferred axis in the universe. You can point in a certain direction of the sky and go, the vector field points in that direction, and the opposite direction it points anti-correlated. So in that case, what you expect is that in one hemisphere of the sky, in one half of the sky, the polarizations will be rotated counterclockwise a little bit, and in the other hemisphere, they'd be rotated clockwise a little bit, okay? We didn't look for that effect. So Nodland and Ralston had claimed to look for that effect and find it with a huge statistical significance. Okay. So I didn't believe that. George didn't believe it. Even though we didn't look at it, and again, if you have ever done a scientific project like this, when you're doing it, you play with the data. You plot it in different ways. You get to know it. You get to know, that point, it always appears over there on the plots and things like that. So it just didn't smell right. And not only, like we said, we didn't expect our original paper to find any effect, much less a space-like effect. That would be very hard to explain. Certainly, it would be much harder to explain with sort of a rolling scalar field, because rather than rolling, you would have a situation where the scalar field was fixed, frozen, but its value would change over space, which is just a little bit weird. I don't know. It could have happened. I mean, yet that's why you have to do it. That's why you have to look at the data. But I was still skeptical. I thought that it was more likely in my Bayesian assignment of priors that they had made a booboo. And in fact, they had. And their basic booboo was the following. Remember, I went to great length to tell you that your expectation should be that the polarization of these radio galaxies is perpendicular to the direction in which the jet is oriented, okay, 90 degrees away. Now, there is an ambiguity here, okay? You can't tell. Polarization is a direction, but it's just a direction modulo 180 degrees, okay? So in other words, you know that there is a line along which the polarization happens, but there's no orientation to that line, forward or backward. So if you rotate the polarization by 180 degrees, it's exactly the same polarization you had before, okay? So when I say it's perpendicular at 90 degrees, 90 or 270 or some multiple thereof. So what Nodland and Ralston did for some reason, which I don't know, they assumed that the natural intrinsic polarization of these radio galaxies was parallel to the radio jet, not perpendicular to it. And so they had a puzzle because, most of them are actually at 90 degrees. And so they thought that the fact that most of the polarizations are at 90 degrees to the jet indicated that it had been rotated by 90 degrees approximately. And then they had to figure out, was it rotated clockwise or counterclockwise? And so they made an assumption. They said, okay, pick a direction along the sky. We're going to assume that in one hemisphere, all the rotations are clockwise. In the other hemisphere, all the rotations are counterclockwise. And then we're going to ask what direction, if you imagine that presumption, what direction fits the data the best, okay? And then they fit a straight line. So here's what you have to visualize. And I'll put a link in the paper to the eventual plot that we made. I'll put a link in the show notes to the eventual plot that I made to show this. What you're asking is, what is the change of the polarization versus how far you are away, okay, versus the distance to the galaxy. And what they assumed, again, is that in one half of the sky, all the polarizations are in one direction, all the rotations. In the other half, it's in the other direction. So if you make a plot on a piece of graph paper, what it's like doing is saying that by hypothesis, by construction, if you divide your graph paper up into 4 quadrants, upper right, lower left, upper left, by hypothesis, the data can only be in the upper right and the lower left, okay? They assumed that all the rotations for galaxies in one half of the sky were clockwise and the other half of the sky were counterclockwise, so they exclude by hypothesis half of the places where the points could possibly be. And they fit a straight line through it and they find a non-zero slope. That's a silly thing to do. That was not a good choice because you are forcing your data to show you an effect. There's no possible way they could have failed to see an effect. And what they should have done is they should have contrasted that effect they claimed to find versus a null hypothesis that was just everything is perpendicular and there are no rotations at all. And so we realized that this was important, and we moved very quickly, and George and I wrote a paper, over the course of a week. And we said, look, here's what you should have done. We can do the analysis of which of these hypotheses is a better fit. Hypothesis 1 is everything's perpendicular. Hypothesis 2 is everything is rotated 90 degrees clockwise in half the sky and counterclockwise in the other half of the sky. Hypothesis 1 is a better fit. There's no effect at all. Okay. So this was fun. This was very exciting. We got our paper published in Physical Review Letters saying that this was not really an effect. The New York Times, as far as I know, never retracted their article, but that's okay. I don't put any big blame on the people who wrote the original paper or the New York Times or anything like that. Mistakes are made, they're corrected. That's how science goes on. All of this is a way of saying that there in the middle of 1997, I suddenly sort of started thinking about polarization and Lorenz invariants and Churn-Simons theories again, okay, and cosmic birefringence, right? So it was at least in my mind. It was not a hot topic in any sense by anyone's stretch of the imagination, but it was something that I started thinking about. And George and I, around that time, wrote another paper on the magnetic field problem as well. So then, as you might know, if you follow the recent history of astrophysics and cosmology, the next year, in 1998, we discovered that the universe is accelerating, okay? Brian Schmidt, Adam Rees, and Saul Perlmutter later won the Nobel Prize for leading two teams to show that the universe is accelerating, which we attribute to dark energy, either a cosmological constant or some form of dynamical energy that is pushing the universe apart, okay? And I'm not going to go into details about that right here. That'd be another podcast, maybe next year. But this saved my life. I mean, it literally saved my career anyway as an academic, because this was something that now, number one, the acceleration of the universe, everyone is interested in this, okay, right? That's certainly intrinsically interesting. You don't blame them for being interested in it. It's a huge game-changing discovery. And number two, I was perfectly positioned to write about it and think about it and do work on it, okay? And I thought it was interesting. I was not making any compromises there. Brian Schmidt was my office mate in graduate school. Adam Rees lived in the office below us. Adam was a recent guest on Mindscape. And I had actually talked to Saul Perlmutter and his group before about different cosmological tests that you could do with Bill Press and Ed Turner. I'd written a review article that was very, very popular about the cosmological constant. With Greg Anderson, I'd written a paper about what is now known as dark energy, even though it wasn't called that at the time. So both on the theory side and on the experimental side, I was in on the ground floor as far as the acceleration of the universe was concerned. So once it was discovered, the acceleration of the universe, it's easy to say, well, yeah, you should work on that. Okay, I mean, Einstein already did the important work. He came up with the cosmological constant in 1917. What are you going to do next? What else is there? And I think that was a lot of the motivation, not the only motivation, but part of the motivation for people thinking about quintessence. Quintessence is just the name that Paul Steinhardt and his collaborators gave to the idea that there is this scalar field that is dynamical, that is changing with time, but very, very slowly, and it pushes the universe apart. It's a dynamical kind of dark energy. So this became a very popular thing to think about, that the dark energy was not just a cosmological constant, an intrinsic energy density in space, but it was a scalar field slowly changing with time. That bugged me right away. Like I got why people were working on it, but as someone, the cosmologists worked on it, the particle physicists rolled their eyes. And the reason why is because they all these models of quintessence were incredibly finely tuned, okay? You may have heard of something called the hierarchy problem. This is a problem for the Higgs boson. The Higgs boson has a mass, and we can measure the mass. It's about 125 billion electron volts. And by all rights, that mass should be enormously larger. The quantum mechanical contributions to that mass, if you sort of separate out the classical value and the quantum value itself is way larger than 125 GeV. So much like the cosmological constant is way smaller than we expect it to be, the mass of the Higgs boson is also much smaller than it needs to be, 10 to the 2 billion electron volts, okay? These quintessence scalar fields are kind of like the Higgs boson. They're scalar fields. They have a mass. That mass gets a contribution from quantum mechanical effects, but their masses are something like 10 to the minus 40 billion electron volts. So if 10 to the minus 2 is small, 10 to the minus 40 is very, very small. Sorry, 10 to the plus 2. If 10 to the plus 2 is small compared to the natural value, which is up near the Planck scale at 10 to the 18 billion electron volts, then 10 to the minus 40 billion electron volts is just crazy small. And furthermore, there are experimental tests. And so, like, because I did care about experimental tests, I knew that if you had light scalar fields, if you had these very, very low mass scalar fields, they're force fields. They should couple to ordinary matter, and people had looked for those couplings. They would violate the principle of equivalence. I'd written papers about the principle of equivalence. Different kinds of materials would couple with different strengths to these new fields, and therefore there would be composition-dependent forces that would make these new scalar fields very, very visible. So even though everyone got excited about thinking about quintessence, I just was a little bit grumpy about it because I'm like, oh, come on, guys, you're being incredibly finely tuned. You're just helping yourself to all these unnatural things. Let's just stick with the cosmological constant. But then I thought about it. And so I said, well, maybe rather than just being grumpy, you should be productive. You should be constructive. You should actually try to fix the problems that these models have. So I said, is there any way to imagine a scalar field that could be quintessence, that could have an energy that suffused all of space and pushed the universe apart in a way to make the universe accelerate without being subject to these constraints from fifth forces? Oh, the other constraint is the constants of nature should be time dependent, okay? This field should couple again to electrons and to photons and things like that, and that should lead to an apparent change in the strength of electromagnetism, in what we call the fine structure constant, the number that tells you how strong electromagnetism is. And people had constrained that. So I actually sat down and I said, okay, if you have these natural values for the coupling of this quintessence field to ordinary matter, how big should the new forces be? How much should the fine structure constant and so forth change? And the predicted changes were bigger by a lot than the best results that people had already used to constrain them. There's a whole fun story about where the constraints come from and so forth. The Oklo natural reactor is something you can Google. OKLO is a naturally occurring nuclear reactor that lets you test the time dependence of fundamental constants of nature. So anyway, the natural coupling constants are ruled out even if you help yourself to a very low mass scalar field. There's a way of eliminating interactions between fields when you don't want them, when you have not seen the experimental evidence for them, and that way is called symmetries. Symmetries will often prohibit certain kinds of couplings between different fields. So if you say, well, I demand that my fields be invariant under this following set of symmetries, then I'm allowed certain interactions and not allowed other interactions, okay? So there is a particular kind of scalar field that can naturally have a very low mass. That's what you want for quintessence, right? Because otherwise it would have rolled to the bottom of its potential instantly instead of taking tens of billions of years. And that kind of scalar field is called a pseudo-Goldstone boson. Jeffrey Goldstone at MIT invented this idea that when you break a symmetry, there's sort of a Mexican hat potential. If you've ever seen these pictures of a potential for two scalar fields that have a symmetry between them, so you can rotate them into each other around a circle, the shape of the potential naturally looks like a sombrero or a Mexican hat. So it's high in the middle, then it goes down to a circle around the edge, and then it goes up again. So when you have that kind of Mexican hat potential, there is a direction in which the field can move on the brim of the hat without changing its potential energy at all. And what that means in particle physics speak is that direction in which the field can vibrate has zero mass. So a Goldstone boson, which Jeffrey invented back in the 1960s, Goldstone boson has zero mass automatically. But if you have, and this happens for things like axions and pions and so forth, which I've already mentioned, if you have almost a symmetry, if you have a symmetry that is pretty good, but is violated a little bit, then you get what is called a pseudo-Goldstone boson, and it's as if you've taken that hat and you've tilted it just by a little bit. So you've given that scalar field, which used to be massless, a little tiny mass by tilting the brim of the Mexican hat. And you might say, well, but if I break the symmetry, why does it help you with a low mass at all? And this was actually all worked out by Gerard de Tooft, Nobel Prize-winning physicist in the 1970s. There's something nice about symmetries, even if they're only approximate. You can naturally have small numbers in theories of quantum field theory if there's an approximate symmetry that protects them. So my point was, if you want to have a quintessence field, you need to have it be very, very low mass. And you can't just say that. You need some reason why it's low mass. So here's a reason why. Maybe the field is a pseudo-Goldstone boson. Maybe there's a symmetry that protects the field from getting a large mass. Okay. So if that's true, you can ask, well, what does that symmetry do to the other interactions? What does that symmetry do to how the field would couple to electrons and photons and other things that I said could be used to rule out quintessence fields more generically? And the answer is it eliminates them. It gets rid of them. You can't have couplings that would change the fine structure constant or that would give rise to fifth forces if you have the symmetries of a pseudo-Goldstone boson. So hooray, it works. This is a particular kind of quintessence field, a particular kind of dark energy field, which could be natural in the quantum field theory sense, which could be something which could be the dark energy without fine-tuning anything. And by itself, that wasn't my idea. There were previous papers by Josh Freeman and other people who suggested that pseudo-Goldstone bosons would be natural forms of dark energy. Okay. My contribution was to say, not only could it make the mass small, it also makes these couplings small. They hadn't investigated that. So I said, it also saves you from the constraints of fifth forces and time-dependent constants. Except there is one interaction, there is one thing the pseudoscalar field can do that is not squelched by the symmetry that it has. And it is exactly the Churn-Simons interaction. Remember, I told you that this Lorentz violating vector field could be thought of as the gradient of a pseudoscalar field. So the pseudoscalar field can naturally couple to electromagnetism in precisely one way without violating this symmetry, and that way is what George and Roman and I had looked at back in 1990, okay? So in other words, my realization was, if you wanted to have a quintessence field to make the universe accelerate, but you wanted it to be natural, you didn't want to sort of just cheat and set some numbers to be very, very small all by themselves, then you could make it a pseudo-Goldstone boson, and it would naturally not just be low mass, but have small couplings, except it would predict there should be cosmic birefringence. The prediction of this model is that there's one interaction that is not ruled out, and you can even estimate its size, and that would predict that throughout the sky there'd be a uniform rotation in the polarization of radio galaxies or any other polarized sources you could imagine, okay? And like I said, you can estimate the size of the effect, and to my delight, the answer was that it's a very, 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 very rough estimate, but it was just below the actual existing limits. So it has not yet been ruled out by actual data. Okay, so I wrote a paper about that. I wrote a couple other papers on dark energy and so forth. I was a hot property on the job market again, right? Not because of me, just because the universe helped me out and sort of by giving me good things to work on, okay? And so I got a faculty job, University of Chicago, and the rest is history, as it were. And so again, you know, there turned out, even though I was sort of hired as an expert on dark energy theory, and I wrote some more papers that were highly cited about dark energy and modified gravity and so forth, as far as we can tell now, the data just say the dark energy is a cosmological constant. You know, the data are much better now than they were in 1998. I collaborated with the high redshift supernova team on one of the very first papers to use this new supernova data to see whether or not the dark energy could be changing with time. And we found that, you know, it could be, but probably not. And that continues to be the case. And the room for it to be changing continues to go down. But it's still there. There's still room for the dark energy density to be changing a little bit. So the idea that dark energy is dynamical rather than constant is still very much on the table, even though its space for being real has diminished just by a little bit. Okay. Meanwhile, other people kept thinking about this birefringence thing. And in particular, a bunch of people, I think Mark Kamiankowski, others, realized that, you know, as wonderful as the radio galaxies were, and people pointed out, by the way, you could do much better than our radio galaxies. Like real astronomers got interested and were able to do much better than we did numerically. You could also use the cosmic microwave background. And, like I said, I had not delved deeply into the physics of the CMB, so I never thought of this because, roughly speaking, sure, the CMB has a little bit of polarization, but how would you ever know what it's polarized compared to, right? It's just out there. It's uniform over the sky. So that's because I'm not an expert. The experts, like Mark Kamiankowski, said, look, there is a relationship between the polarization of the cosmic microwave background and the temperature of the cosmic microwave background. The temperature is roughly constant everywhere, but not exactly constant. And that's the whole industry of measuring anisotropies in the cosmic microwave background, measuring the tiny little changes in temperature from place to place. And what Mark knew, because he was in on the ground floor in terms of the CMB polarization, was that there is a relationship, a predicted correlation between the direction of the polarization of the CMB and the pattern of temperature anisotropies in the CMB. So he and his collaborators wrote some papers on potential tests for cosmic birefringence using the cosmic microwave background. And I was just in the background cheering them on. I didn't do anything with it myself. And Brian Keating, who I mentioned, is a cosmologist at UCSB, UCSD. He's in San Diego. I was in Santa Barbara. So Brian has actually developed a specialty in looking for cosmic birefringence. He is a cosmic microwave background experimental physicist. He was one of the first people on the BICEP collaboration, and he's now one of the leaders of the Simons Observatory. And one of their big projects will be looking for cosmic birefringence. Okay, so people know about it. People have looked for it, but it's hard. And I want to emphasize that it's very, very hard because, and even though in some sense the cosmic microwave background is a wonderful source of data, it's also, the effects are all very, very tiny. Let me. I know I'm running long already, but let me deviate a little bit to tell you another little side story that will illustrate what I mean. When I got to Caltech in 2006, I took on a new student, Lottie Ackerman, and she and I collaborated with Mark Wise, who is a senior person at Caltech, on asking the question, what if inflation in the early universe had happened in different directions with different speeds? Okay, so ordinarily inflation is something where in the early universe, there's kind of super dark energy. It pushes everything apart and smooths everything out. So we said, what if inflation were anisotropic? What if inflation happened more rapidly in one direction than in the other two perpendicular directions? So nothing to do with birefringence or anything like that, but we asked what would happen. And we found that there's a prediction for the microwave background that there would be a sort of a very particular pattern of variation of the amount of variation, right? So there's variation in the temperature, but imagine that overall variation in temperature from place to place looked bigger in one direction of the sky than in the perpendicular direction of the sky. Okay, that's the prediction that we made. And it turns out that no one had looked for this. They'd looked for certain versions of it, but not the version we actually predicted. And then when you did predict it, what we predicted, again, was that there's an axis along which the fluctuations are either bigger or smaller than in the perpendicular plane. So it's what we call a quadrupole power asymmetry. And no one had looked for this. So as soon as we published our paper, Lottie and Mark and I, people did look for it, and they found it right away. Now, why did we not become famous, and why haven't you heard of this? Well, because it's a very natural systematic error for a cosmic microwave background satellite. If you think about what a CMB satellite does, it looks at the sky, tries to look at the whole sky, but it doesn't have one big antenna that looks at the whole sky at once. It has a pattern that it sort of covers the sky as it sort of spins around. And it's kind of like a peeling the orange kind of pattern, right? You go in some circle, but that circle slowly rotates. So you imagine that there's a lot more coverage on one pole and the other pole than there is on the equator, okay? And that turns into a very natural systematic error that can fool you into thinking that you actually see the kind of effect that Lottie and Mark and I predicted. There you go. All of this is just to say that finding tiny effects in the cosmic microwave background is very, very hard to do. People have tried it. They haven't found it. Okay. Now, here we are, November 2020. I know I'm saying this in December 2020, but what I mean is in our story, we've caught up to November 2020, and there is an announcement of this new paper in Physical Review Letters by Minami and Komatsu. I don't know Yuto Minami. Hi there, Yuto, if you're listening. I don't know. I've never met you. Ichiro Komatsu is a big name. He's a very, very accomplished cosmic microwave background physicist, someone who you should take seriously, right? So it's not like nobody's in the middle of nowhere or just saying crazy things. These are people who know what they're doing. And they have looked very carefully at data from the Planck satellite, okay, which looked at the polarization of the microwave background. And I will read you what they say. This is the abstract of their paper. We search for evidence of parity-violating physics in the Planck 2018 polarization data and report on a new measurement of the cosmic birefringence angle. ... We show that systematic errors are effectively mitigated, and we find that the polarization angle is 0.35 degrees plus or minus 0.14. So 0.35 plus or minus 0.14. That excludes the idea that the angle is zero at 2.4 sigma, which is good but not great, honestly. Okay. So what they're saying, and they're, extremely careful, doing everything right. They're not overclaiming. They're saying, look, we found a little hint of something. It should be followed up. We should do better. So I have no idea what to think about this. In other words, I'm not going to tell you this is true and it's going to be very exciting and we've discovered the dark energy. I'm also not going to tell you it's wrong and it was a mistake and they just made another boo-boo, okay? These folks know what they're doing. They've analyzed the data. I believe they've analyzed it to the best of anyone's ability. But a 2.4 sigma result is just not yet quite enough to take as proof of anything, certainly, maybe even as evidence. So in particle physics, we have the standard that you need a 3 sigma deviation to get evidence for something, and a 5 sigma deviation to get a discovery of something. So to get the Higgs boson, you needed a 5 sigma result. Sigma is the standard deviation. It's the amount that is different from your measurement to the hypothesis that the effect isn't there at all. So you want more and more sigmas, more and more deviation from the expectation to be able to say, I've definitely found something. It's not just a random error. That's just not random numbers fooling me, okay? So 2.4 sigma is 99.2% confidence. That sounds pretty good, but the problem in any of these things is you're always looking for many, many effects, okay? So if you find an effect that is only 1 out of 100 chance, well, you've probably looked for 100 effects, honestly, when you're honest with yourselves over the course of your life. So you should find things like that. So 2.4 sigma is at exactly that tantalizing amount of significance where it's enough to take seriously. It makes you sit up a little more straight in your chair, but not yet enough to say, oh, that won't go away. That's a real thing. But one of the reasons why it's very, very interesting is because, and I talked about this on Twitter a little bit also, when we did the Higgs boson, we crept up on the royal we, the physics community, the very, very hardworking experimental physicists at the Large Hadron Collider. You creep up on this significance, right? There's an announcement, there's something there at 2 sigma and 3 sigma and eventually 5 sigma, et cetera. But look, everyone thought it was going to be there, right? I mean, the Higgs boson was part of the standard model of particle physics. You needed to have it work, okay? So once you were at 3 sigma, people were like, oh yeah, we're going to get there. In fact, literally, I got a book contract out of that, right? When I wrote The Particle at the End of the Universe, I got my contract right after they had gotten 3 sigma because it wasn't my idea to write that book. My editor said, the world needs a book on the Higgs boson because they're going to find it, right? They're going to find it. And I said, yeah, they're going to find it. And he said, well, we need a book. We need a book by someone who can write, who knows the physics, who can write fast. By the time, we want the book published by the time they discover it. Well, that didn't happen because they discovered it only like 6 months later. But at least it came out for Christmas. That was very nice. But the point here is that there is a joke that has some truth into it, that experimental findings need to be confirmed by theory. And if you're really hardcore, you would laugh at something like that. You go, no. Theory needs to be confirmed by experiment. You should believe your experimental results. But in the real world, in the world where we all live, some experimental results pan out and some don't. And you need to sort of have a way of judging whether you put credence in the different experimental results. When people at CERN discovered that neutrinos are moving faster than the speed of light, they had good statistical significance, but no one believed them because it just didn't fit into our theory at all. And eventually they found they just made a mistake. So there's something like the Hubble tension, okay? Remember, I talked with Adam Rees on the podcast about this discrepancy between ways of estimating the value of the Hubble constant today from data nearby, from stars and supernovae and things like that, nearby galaxies, versus from data in the early universe in the microwave background. And at the pure level of statistical significance, it's quite noticeable, this discrepancy, but there's no really good theoretical explanation for what it would be. So people are a little reluctant. I'm a little reluctant to take it too seriously. When Adam and his friends in 1998 said the universe was accelerating, I and many other people instantly thought it was right because we had a very obvious explanation for it, the cosmological constant. And in fact, that solved a whole bunch of other pre-existing problems in cosmology, just made everything snap together in a nice way. So this claim from Minami and Komatsu is kind of in between. We have if it's true that there's cosmic birefringence, if it's true that the polarization of photons in the microwave background have all been rotated a little bit, I don't know, maybe clockwise, I don't even know what direction it's in. It's a positive number, so maybe clockwise by 0.35 degrees. That's easy to explain. I explained it. I put forward a theory that would predict almost exactly that, within the same order of magnitude numerically, not just that the effect exists, but the magnitude of the effect, okay? But okay, it's still nowhere near as robust as just saying it's a cosmological constant. So the evidence is very, very tentative. So, the Hubble tension, which would be a big deal, I would say the evidence for it is pretty solid, except that the theoretical explanation is completely lacking. This cosmic birefringence claim, the evidence for it is, it's suggestive, but not nearly as well established. Only one group, two people, right? You would like to see independent analyses get the same answer. But at least we have an answer. We have a theoretical explanation to hand if it turns out to be true. And in fact, by the way, I think, just because I am me and I know what I did here, it's completely possible that there are other theoretical explanations that are not mine, right? So it might be that there was I think that there are already papers saying that, well, there could be some kind of pseudo-scalar field in the early universe, not now, not a quintessence field, but early universe pseudo-scalar fields that could induce a polarization that would be rotated in exactly this way. So, and that's as it should be. If this effect turns out to be true, don't just believe the first possible explanation. Open your mind, look for all the possible explanations. So, just to put all of this in context, I am very, very, very much rooting for this to be true. I would love for this to be true, but I know that I would love for it to be true, that there is some birefringence out there, and therefore I need to correct for that, right? I need to be careful not to let my enthusiasm get the better of me, and I should adopt a proper skeptical posture, which is more or less what I've done. If you forced me to bet at even money, I would bet that this is going to go away. I hope it doesn't, and there's certainly it's more than 1% chance that it's not going to go away. Let's put it that way, between 1% and 50% chance. So I think this is a good sort of, this whole thing, I've gone on a long time, I know I tend to do that, but I think it's a good illustration of a whole bunch of different ways in which real theoretical physics gets done, okay? Real science gets done. Obviously, a lot of the heavy lifting here is done not by theorists, but by the experimenters collecting the data and analyzing it. It's not a lone genius sitting in their study, in their armchair, coming up with brilliant ideas or anything like that. It's highly collaborative, right? None of this would have happened. The first paper with me and George and Roman, we all brought something to the operation. Like, Roman had the mathematical chops. He had the idea, Churn-Simons theory in 3 dimensions. George had the, down-to-earth realism and the astrophysical chops to say, like, we should try to do this in the real world, and I know how we can test it. And, but they're both, I don't think either one of them had typed in a lot of data or made any plots recently in their lives. So you need a graduate student around who is willing to, the nice thing about graduate students is they're not experts at anything, therefore they can do anything because they know they have to learn whatever it is you ask them to do, whether it's, do an integral or make a plot or learn about topology or whatever. It's all new to them when you're a graduate student. So you say, okay, I'll do it, right? When you're an old professor, you're good at some things already. And the idea of doing something brand new seems intimidating and tiresome because I can just do the old thing that I did my whole life and became famous doing, right? So that was my role. back then. I typed in the data, and I did catch up, by the way, just so you know. I caught up, so I understood the theory behind it, and could push that theory forward later on. And it didn't go away. It was an interesting idea. Many people have followed up in many different ways. I kept thinking about it. We've put the idea to use in other contexts, like magnetic field generation in the early universe. Experimentalists are always very, very happy when you make predictions for something, no matter how crazy those predictions are, because they can go test them. So experimentalists have been thinking about birefringence now for a long time, and maybe the state of the art has gotten so good that we're able to find this thing that has been there all along. And maybe this is a clue to what is 70% of the energy density of the universe, right? The dark energy is approximately 70% of the total energy density of the universe. So this could be the first strong clue that it's not just the cosmological constant, that it's a field, a pseudo-scalar field that is pushing around photons and their polarizations, an absolute, unmistakable, if it turns out to be true, unmistakable example of physics beyond the standard model of particle physics, because this kind of rotation just wouldn't exist in conventional physics. So stay tuned. 2020 gave us something good, right? There you go. We got that out of it. Maybe 2021, some other people will analyze it and show that it's even more significant, and the significance will creep up from 2.4 to 3.4 and keep going up. If that happens, I promise you at some point I will do another podcast explaining to you what it all means. Okay. Thanks for listening. Thanks for listening all year long. It's been yet another wonderful year of Mindscape. I look over the people who have appeared on this podcast, and no credit to me, but oh my goodness, we've had some really good people on the podcast. People who are both good because they're famous and big names, and I'm amazed that they agreed to come on the podcast, but also people who you've never heard of before and yet gave tremendously good podcast interviews because they have interesting things to say. I always say that I try to mix up the podcast guests in terms of not just fields, but level of fame and level of seniority and things like that. And so far, I think that's working. I like it that no one knows ahead of time what the next subject is going to be. And, there's people who go, oh, yes, I've been waiting for that person. And a lot of people you go, I have no idea who this is. And then you listen and go, wow, I should know more about them. I should read their books. If you search on Twitter, I recently did a Twitter thread on all the books from this year's podcast guests who have books out this year. It's a long list. There's a lot of very interesting books. I originally hoped to make it even podcast guests from previous years if they had new books out this year, but that just became overwhelming. Too many books out there, too little time. But that's good. We should read. We should get better. We should get smarter. Hopefully, this podcast here at Mindscape is doing its little tiny part to make us all think a little bit more, make us all a little bit smarter. So I hope you had a good year. Hope for even better things the next year. Talk to you in January. Bye-bye.